So this is a review of everything we learned about evolution operators. First thing we learned was that there's something we would like to observe. So an example of observable could be a velocity at point x. So here you are in the state space. At every point of that state space, there is a law of motion that says that in delta tau, I'll move Vx in direction delta t. So reasonable observable would be to find out, what is the average velocity. The way to proceed is to define integrated observable. You went for time t, and you observed your d-dimensional velocity field at that point in state space. And we're assuming autonomous flows, meaning that vector field only depends on where you are. And what a trajectory does is it explores some part of the state space. This observable has a name. Integral velocity is the positions. So where we are at time t with respect to where we are at time 0. The first thing we can do experimentally, numerically, we can compute time averages. One over t, our observable per unit time, but that is just x at time t minus x times 0. Imagine that your motion is somewhat complicated. So after time t, you don't get as far as though you were shooting with the gun on a straight line. Then you can define the mean velocity. Now, this always depends on the initial point. So this average really also depends on the initial point. For chaotic system, these averages are the same for generic points, but in principle they belong to the initial point. For that reason, you want to also define a space average. For example, space average of where you are at time t, or how far you have gone in time t. That is an integral. You want average of 1 to be 1. So divided by the volume of the state space. You start every place at every point, and you advance for time t, and you find out what the average advance of everybody is. In physics, this is a necessity because we're not able to prepare infinitely precise initial points. So we're always looking at evolution of volumes of points. So that's a space average. In situation where we have the times much longer than Lyapunov time for the system, so we can't control the evolution system, and your precision is finite, so we cannot control initial conditions, then we want to average over everything. So I call this expectation value. But now we'll start every place and take time off to infinity. So this is just property of this field as defined over the whole volume. And it's 1 over spatial integral. And then we know the time average already. Long times, tells you how far you got if you started at x0, what the average velocity is for all starting points, totally sensible, observable. It says, how fast I'm moving, and this says how fast I'm moving on average. So that's all totally straightforward and humdrum. The only problem is that at least I'm not aware of any good theoretical tools to compute this. So we think about it again, and we think about it using the tools of statistical mechanics.